Here we're going to look at another integration by parts example. So you look at an integral like this and you probably at least try substitution, or at least acknowledge why substitution wouldn't work. And I try to point this out to my students. If this was a cosine of 3t squared, when you take the derivative of 3t squared, you're going to get some number with times t, which can be manipulated to make the substitution work if you let u be that thing, 3t squared. But that's not the case here. So you have to sort of re-examine how you view this integral. So you'll notice it's the derivative of two functions, and I'm going to use integration by parts. So let's just remind ourselves what that looks like. So the integral of u times dv is equal to uv minus the integral of v du. So what we have to do is make a good choice on what to let u and dv be up here. So you want your u to be something whose derivative gets simpler. So I'm going to let u be the 2t, and I'm going to let the dv be the cosine of 3t dt. And then we take the derivative of this left piece, both sides, so that means du equals 2. And then we take the antiderivative of this other side. So the antiderivative of cosine is sine, but I've got to correct for that 3 that would result from the chain rule by multiplying by a third. And now I just apply the formula. So this integral up here again, that was my u, that was my dv. That's going to equal uv, so that's 2t times a third sine of 3t uv minus the integral of v times du, which is 2. Alright, and so what you can do is, I might factor out the constant 2/3. I might factor that out. So this ends up being 2t over 3 sine of 3t minus 2/3 the antiderivative of sine of 3t dt. And so now we've made this problem simpler. And the reason we have is because even though we have this other integral to deal with, we can figure out the antiderivative of sine of 3t probably just by doing it mentally, or you can do u substitution on the 3t. But I would probably just say, okay, the antiderivative of sine is negative cosine, so negative cosine of 3t, but I need to correct for that 3 that would come out from the chain rule, so I'm going to times by a third. I'll put a plus c, and then I guess I'll write my final answer as 2t over 3 sine of 3t, and this becomes, I got a minus 2/3 times a 1/3 times a negative 1 out here, so that's going to be a positive 2/9 cosine of 3t plus c. And there's my final answer. So one thing to point out is that usually you get answers that are kind of crazy, and it's not necessarily worth checking them. I guess if you have time, you can take the derivative of this thing and see that you get 2t cosine of 3t. But really the thing to acknowledge is the choice you made in terms of what you wanted to be u and dv. And this time the choice was correct because this integral that resulted was easier than the original. And as long as that happens, then you're doing it correctly. Let's try another example. So here we have the integral of x squared times e to the x. So I can't use a substitution. So you might have thought, well, let the u be x squared, but there's no way that that's going to, once you take its derivative, there's not going to be nowhere to substitute its derivative into the function, because that x by the e is in the exponent. It's not down below. So we should let our u be, so I'm going to write down the formula again for integration by parts. So I'm going to let my u be the x squared and the dv be e to the x dx, because the derivative of x squared is simpler than x squared, and the antiderivative of e to the x is totally manageable. So the derivative of this left part is going to be 2x dx. And the derivative of the right part is, the antiderivative of the right part is v equals e to the x. And so now we apply the formula. So this integral up here is equal to uv minus the integral of v times du, which is 2x dx. So I'm going to squeeze the 2 in here, the x here, and the dx there. Okay, so doesn't look like it helped a whole lot, but it did. I basically have the same integral I had originally, except it's x instead of x squared. So we would have to use integration by parts again on this problem, and it's, admittedly annoying. However, I kind of rigged this so if you look at a prior video, we've already done this, right? If you let your, I should probably use a different letter than u, but like maybe if you let like w be x and d, dt be e to the x dx in this problem, you're just redoing what I did in the last video, and you'll end up getting x squared e to the x minus 2 times what we got to be the antiderivative of x e to the x, which was x e to the x minus e to the x, all that with a plus c. So I don't mean to cop out on that, on doing that problem. It's just we already did it. And I'm going to show you a trick to do. There's a trick called tabular integration, which would absolutely be the way you'd want to do this problem in the future anyway. So I'll redo it then. But the point of this was that you started with an integral that was somewhat hard. You applied integration by parts. You got a new one that was same method, but at least somewhat less hard because you knocked that degree down by 1. Of course, if this was x to the 5th e to the x, we certainly don't want to apply integration by parts over and over. That's why I'll show you a nice, a different method that would be applicable to this type of problem.